So let's start discussion today. So in the last session we have started discussing logistic regression and we have seen the hypothesis for logistic regression, which is a sigmoid function or which is also known as a logistic function. Today we are going to continue our discussion with respect to logistic regression, and we are going to discuss about the decision boundary and the cost function for logistic regression. So let's see what we mean by decision boundary. As we have stated earlier, the logistic regression is represented with the hypothesis h theta x having the form g of theta transpose x. So our hypothesis in logistic regression is different than the linear regression. In linear regression, we had a hypothesis of the form h theta x equal to theta transpose x. Whereas in logistic regression, we defined our hypothesis h theta x as the function of theta transpose x. So it is g of theta transpose x, right? And we had an interpretation of our logistic regression hypothesis, like this hypothesis is giving us the probability that y is equal to 1 given x parameterized by theta. So we said that this hypothesis h theta x is giving us some value, and that value is interpreted as the probability that the class is 1, probability that y is equal to 1 given x, that is my input, parameterized by theta, right? And also we have mentioned that our function logistic regression hypothesis is of the form g of z, and this is represented as 1 divided by 1 plus e to the power minus z. So this function is known as the logistic function or the sigmoid function. And we have seen how this function looks like. So if we plot this g of z against z, then we are getting a plot like this. Okay, so my g of z or my hypothesis always lie between the values of z, the values of g of z 0 to 1. So always my hypothesis is giving me some value between this range 0 and 1, right? So we had a discussion in the last session about all those concepts. Now we are going to extend this discussion further. We are going to predict the class of the sample as 1. So we are going to predict y equal to 1. If my h theta x is greater than or equal to 0.5. So this g of z is actually nothing but our h theta x, our hypothesis. Correct? And what this z is actually theta transpose x. Am I correct? Are you getting me?
Yes, ma'am.
So this is our sigmoid function. We have plotted this sigmoid function. On x-axis we are having z, on y-axis we are having g of z. Okay, on y-axis we are having this g of z. Okay, and the value of g of z always is in the range 0 to 1. Okay, this g of z is nothing but our hypothesis h theta x, right? And this z is nothing but theta transpose x, right? So we are going to predict the class of the sample as 1. So this 0 is my class label, this 1 is my class label. So I am having two classes, 0 and 1. So my sample is of class 1 if h theta x is greater than or equal to 0.5. What does this mean? This plot is actually my h theta x, right? And this threshold or this value is say 0.5. Right? So this is my 0.5. So if g of z or if h theta x, this is my h theta x, this plot is h theta x. So if h theta x is equal to 0.5 or if h theta x is greater than 0.5, so this range of values 0.5 to 1. So if this h theta x is greater than or equal to 0.5, I am going to predict the class label as 1. Right? Otherwise, if h theta x, so this is my plot h theta x. If h theta x is less than 0.5, then we are going to predict the class label y equal to 0. Right? So if my hypothesis value is evaluated in this range, upper range 0.5 to 1, including 0.5, then we are going to label our sample as class 1. Otherwise, if my h theta x lies in this range 0 to 0.5, then we are going to label our sample as class 0, y equal to 0. Meaning, so when I'll be having this h theta x or this g of z equal to or greater than 0.5, when my z value is greater than or equal to 0, when my z value is greater than or equal to 0, my g of z is going to be greater than or equal to 0.5. Right? So if z is towards this side of 0, if z is equal to 0 or greater than 0, then our h theta x or our g of z would be greater than or equal to 0.5. Do you agree with me? Just look at this plot. Right? So we can infer that, what does this mean? Z is greater than equal to 0, then g of z is greater than equal to 0.5. We can interpret this as h theta x. G of z is nothing but h theta x, and this h theta x is nothing but g of theta transpose x. Right? H theta x is nothing but g of theta transpose x. So if my z is greater than or equal to 0, then g of z is greater than or equal to 0.5, and I can interpret it in this way also. My h theta x or my g of theta transpose x is greater than or equal to 0.5 whenever my theta transpose x is greater than or equal to 0. So this z is nothing but theta transpose x. So if my theta transpose x is greater than or equal to 0, then I'll say that my h theta x is greater than or equal to 0.5. So simply I'm going to predict y equal to 1 if h theta x is greater than or equal to 0.5 or theta transpose x is greater than or equal to 0. So if theta transpose x is greater than or equal to 0, I will label the sample as class 1 sample. Right? So this z is nothing but theta transpose x. So you may look at this plot as theta transpose x against h theta x. Okay? Similarly, When I'm going to predict y equal to 0, I'm going to predict y equal to 0 if h theta x is less than 0.5. H theta x is less than 0.5. And when h theta x will be less than 0.5, obviously whenever my theta transpose x is less than 0 in this region, whenever my theta transpose x is less than 0, or in other words, if my z is less than 0, my g of z will be less than 0.5. Right? This g of z is nothing but my h theta x. So I'm going to label my sample as y equal to 0 when h theta x is less than 0.5, and when h theta x will be less than 0.5 whenever my theta transpose x is less than 0. Right? So simply just remember that we are going to label the sample as class 1 sample when my h theta x is greater than or equal to 0.5 or my theta transpose x is greater than or equal to 0. And we are going to predict our sample belonging to class 0 when we are having h theta x evaluated as less than 0.5, and when it will happen whenever my theta transpose x is less than 0. Then we are going to predict the sample belonging to class 0. Got it? If you have any doubt, please let me know. Yes. Have you understood the concept?
Yes, ma'am.
So whether it is clear when to label the sample as class 1 and when to label the sample as class 0 based on this sigmoid function. Yes, any confusion?
No, ma'am.
Okay, so let's proceed now. Okay, so as I stated, we are going to talk about a concept known as decision boundary. So let us assume that we are having some training data set available with us, and the training data set includes the examples belonging to two different classes. So we are having class 1 samples and we are having another class samples, right? So I may say that one class is class 0, another class is class 1. Okay, every sample is being described with two features x1 and x2. So each sample is associated with some feature value x1 and some feature value x2. So these samples are described with two features x1 and x2. Right? So we have plotted here our training data set. So we are having these samples belonging to two different classes. Okay, now let's assume that we are defining our hypothesis h theta x as g of some, so it's in general, how we are defining our function in logistic regression, how we are defining our hypothesis h theta x in general. In general, we are defining it like h theta x equal to g of theta transpose x. G of theta transpose x. Right? Now, as in our example, we are having two features. We are having here x1 and x2, two features. Okay? And let us assume that the hypothesis is defined here like g of theta 0 plus theta 1 x1 plus theta 2 x2. So this term theta 0 plus theta 1 x1 plus theta 2 x2 is nothing but my theta transpose x. Right? This is nothing but theta transpose x. So let us assume that we are having this expression, this hypothesis g of theta 0 plus theta 1 x1 plus theta 2 x2. In fact, Using logistic regression, we want to once again come up with the optimal values of theta 0, theta 1, theta 2 in this case, or the parameter values. But now, just to understand the concept of decision boundary, let us assume that we have come up with some values of theta 0, theta 1 and theta 2. Let us assume that we have come up with the value of theta 0 that is equal to -3, value of theta 1 that is equal to 1 and value of theta 2 that is equal to 1. So our parameter vector theta would look like -3, 1, 1. So this corresponds to theta 0, theta 1, theta 2. So my parameter vector theta is having the values -3, 1, 1. So this is just one example for illustration. So obviously my function, my hypothesis would be like h theta x equal to g of -3 plus x1 plus x2. Do you agree with me? Any doubt so far?
No, ma'am. Ma'am, how we are taking this theta here?
Yes, that is what I stated. Right now we are assuming just to understand the concept. Later on we are going to discuss the algorithm to come up with these parameter values, because that is what our goal is. Right? So similar to the algorithm that we discussed for linear regression, we are going to discuss the algorithm, right, to come up with these parameter values for logistic regression also. Just for the sake of understanding, we are right now assuming the values of theta 0, theta 1 and theta 2. Right? And that is why I mentioned here that with the assumption we are having this parameter vector with us, theta -3, 1, 1. So our hypothesis h theta x becomes g of -3 plus x1 plus x2. Right? Now, let us apply the knowledge that we have. We mentioned in the earlier slide that we are going to predict the class y equal to 1 if h theta x is greater than or equal to 0.5. And when it happens when our theta transpose x is greater than or equal to 0. That we have seen already. So the same rule we are going to apply here, right? So we are going to predict y equal to 1. We are going to predict y equal to 1, that is class equal to 1, if h theta x is greater than or equal to 0.5. Now, what is my h theta x? My h theta x is g of -3 plus x1 plus x2. Right? And in other words, we mentioned that we are going to predict y equal to 1 if h theta x is greater than or equal to 0.5, or in other words, we may say that if my theta transpose x is greater than or equal to 0, I am going to predict the sample as y. So what is my theta transpose x here? This term is my theta transpose x. So my theta transpose x is -3 plus x1 plus x2. Right? So if this theta transpose x, that is -3 plus x1 plus x2, is greater than or equal to 0, then we are going to predict the label as y equal to 1, or we are going to predict the sample as y equal to 1. Now, if we simplify this expression, -3 plus x1 plus x2 greater than or equal to 0, we may say that we come up with this expression as x1 plus x2 is greater than or equal to 3. x1 plus x2 is greater than or equal to 3. Now, if we look at this expression is right now the expression for a straight line, right? x1 plus x2 is greater than or equal to 3, or rather we may say x1 plus x2 equal to 3 is the expression for a line. x1 plus x2 equal to 3 is the expression for line. And if I try to plot that line in this space, then how my line would look like? What we have, x1 plus x2 equal to 3, right? So if I put x1 as 0, then obviously to come up with x1 plus x2 equal to 3, my x2 must be 3. So this point. So if I get 2 points, it is possible for me to draw a line. That is why I am explaining. And if I put x2 equal to 0, if I put x2 equal to 0, then obviously my value of x1 would be 3. So this point, right? So I am having the point 0, 3 and 3, 0. So if I try to draw a line, then this x1 plus x2 equal to 3, this line would look like this. Are you getting me? Yes? Are you getting me?
Yes, ma'am.
Fine. So, if I am having such kind of a line, then what I stated, I am going to predict y equal to 1 if h theta x is greater than or equal to 0.5. And this has provided me with this expression, x1 plus x2 is greater than or equal to 3. So, when this expression will be satisfied, x1 plus x2 greater than or equal to 3. We have drawn a line that satisfies the expression x1 plus x2 equal to 3. So, if I move on with the values of x1 beyond this or values of x2 beyond this, so in this region, I'll be having x1 plus x2 greater than or equal to 3. Do you agree with me? In this region, I always will have x1 plus x2 greater than 3 towards this side of this line. So, if I am having a sample towards this direction or towards this side of the line, then I am going to label the sample with class y equal to 1. Okay, and my h theta x is less than 0.5, then what will happen? If h theta x is less than 0.5, that means if theta transpose x is less than 0, then I come up with this expression x1 plus x2 less than 3. x1 plus x2 less than 3. So if this expression is satisfied, then I'll say that my class of the sample is y equal to 0. So which is this region that satisfies this expression x1 plus x2 less than 3? Obviously, this region is this side of the line. So below this line, I am having the expression, or I am having the region that satisfies this expression x1 plus x2 less than 3. So towards this side, I'll say that my class is y equal to 0. Okay, and this line, this pink line that separates these two classes is known as the decision boundary. This pink line that actually separates these two classes is known as decision boundary. And in this particular example, this decision boundary is denoted with this expression x1 plus x2 equal to 3. Right? So this line is our decision boundary. So towards one side of my decision boundary, I am having the class, or I am having the samples with class label y equal to 1. and towards other side I'll be having the samples with class label y equal to 0. Right? So this is how we may interpret this hypothesis. We may come up with our decision boundary, and based on this decision boundary, it is possible to classify the samples. So if unknown sample comes in, simply what we are going to do, if unknown sample comes in, simply we are going to compute this x1 plus x2. We are going to compute this x1 plus x2. This is our decision boundary, right? So let us assume that I have come up with one sample here. So this is unknown sample. Let us assume that this is unknown sample. Okay, and this sample is having x1 value, that is say 5. X1 feature value is say 5 and x2 value is say 2.5. X2 value is say 2.5. So obviously what I am going to do is I am going to compute this expression x1 plus x2. So what this expression will provide me, x1 is 5 plus x2 is 2.5. So it will give me 7.5. So this 7.5 is greater than 3, and that is why I declare that this unknown sample belongs to class 1. Right? Similarly, if I am having the unknown sample in this region, suppose I am having unknown sample here at this place. Let us assume, then suppose x1 value is 2.2. Let us assume x1 value is 2.2. Okay, and y1 value is say 0.2. Sorry, x1 value is 2.2 and x2 value is say 0.2. So once again what I will do, this is my unknown sample. So once again what I will do, I'll evaluate my decision boundary, or I will evaluate this expression x1 plus x2. So what is the value of x1 plus x2? 2.2 plus 0.2. So it is 2.4. So 2.4 is less than 3. So as this is evaluated as less than 3, obviously I am going to declare that this unknown sample belongs to class y equal to 0. Are you getting me? Any doubts so far? Got the concept?
Yes, ma'am.
Fine. So this is how we are going to define our decision boundary. So decision boundary is actually differentiating between two classes. Right? So towards one side of our boundary, we are having class 1. Towards other side of the boundary, we are having other class, say class 0. Okay? May I proceed?
Yes, ma'am.
Fine. Now, let us proceed with a non-linear decision boundary. So we talked about a linear decision boundary. That means a line that is treated as the decision boundary to segregate the samples between two classes. Now, let us assume another example. So what we have is, once again, we are having the samples, those belong to two different classes. The samples belong to two different classes. But if we look at this figure, we are having the samples spread like this. So obviously you may find that we may not have a line that separates these samples. We may not have the line that separates these samples. Okay, so obviously we should come up with a non-linear function that can be treated as the decision boundary. So once again, let us assume, once again we are assuming, right? that our h theta x, that is the hypothesis, is of the form g of theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x1 square plus theta 4 x2 square. See here, if we look at these samples, we know that the linear function will not help us to separate out or to segregate the samples in two classes. So if I go with such kind of a linear function, theta 0 plus theta 1 x1 plus theta 2 x2, it may not help me because this is a function, linear function. So linear function will not help me, and that is why we are assuming that we are having a function h theta x of the form g of theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x1 square plus theta 4 x2 square. So we have added two quadratic terms over here, x1 square and x2 square. These are the quadratic terms. Those we have added, right? So this function, this entire function is now non-linear function, right? Now, once again, we are assuming that our parameter vector is having the values -1, 0, 0, 1, 1. We are assuming our parameter vector theta is having the values -1, 0, 0, 1, 1. What does this mean? This theta 0 is -1. This theta 0 is -1. This theta 1 is 0. This theta 2 is 0. We are assuming these values. Theta 3 is 1 and theta 4 is 1. Okay. So if we assume those values, then applying our knowledge, we are going to predict the class y equal to 1 if h theta x is greater than or equal to 0.5. So obviously this expression is my theta transpose x, right? So h theta x is greater than or equal to 0.5 when my h theta x is greater than or equal to 0. So this is my theta transpose x. So what is my theta transpose x? -1. This will become 0. This will become 0. So -1 plus x1 square plus x2 square. So -1 plus x1 square plus x2 square is my theta transpose x. So I'm going to predict y equal to 1 when my theta transpose x is greater than or equal to 0. Right? So just by rearranging this expression, we may say that we are going to predict y equal to 1 if x1 square plus x2 square is greater than or equal to 1. x1 square plus x2 square is greater than or equal to 1. Now, if we look at this, if we consider only the equality in this expression, so this will give me x1 square plus x2 square equal to 1. x1 square plus x2 square equal to 1. And if we look at this expression x1 square plus x2 square equal to 1, we know that this expression is the expression that denotes a circle with radius 1. Am I correct? x1 square plus x2 square is equal to 1. x1 square plus x2 square is equal to 1. So this expression is the expression for a circle with radius equal to 1. Correct? So if I plot this circle now, I am having such kind of a plot. Circle with radius 1. Right? And in this situation, I am going to say that this is my decision boundary. So x1 square plus x2 square equal to 1 is my decision boundary. So based on this decision boundary now, when I am going to say that The class is y equal to 1. The class is y equal to 1 if x1 square plus x2 square is greater than or equal to 1. So all the samples, those lie in this direction of the circle or outside the circle. Then I'll say that the class is equal to 1. Right? And as against this, say that my class is equal to 0 when exactly opposite happens. So if x1 square plus x2 square is less than 1, then I'll say that the class is equal to 0. So within this circle, if I'm having a sample within this circle, then I'll say that the class is equal to 0. Right? So this is my decision boundary that separates out the samples from two different classes. And this decision boundary is non-linear decision boundary. Got it? Yes? Any doubt so far? Yes? Any doubt?
Higher degree polynomial equations. In that case, how we will decide decision boundaries?
Um, Hello, will you please once again repeat your question?
Ma'am, if we have given higher,
You are not audible. Hello?
hello ma'am,
Yes.
ma'am, if we have given higher degree polynomial equations,
Yes.
in that case, how we will decide decision boundaries?
Yes. 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 See, this is just the demonstration for comparatively simpler non-linear decision boundary, that is a circle. Okay, and this circle can be represented with such kind of a simple expression. Okay, now we may have the hypothesis, which is, just look at this hypothesis. We may have the hypothesis of higher degree polynomial, right? So we are having
Okay.
two features only, x1, x2. But just look at it, we may have any degree for this polynomial. So we are having many such terms included, and such kind of a function actually may provide us very non-linear hypothesis, very non-linear hypothesis. So I may get a boundary like this, right? And if I am having such kind of a boundary, then also it is possible for me to segregate the samples in two classes. The samples inside this region may be y equal to 1. The samples outside the region may be y equal to 0. Right? So it is
Yes, ma'am.
possible that we may have the polynomials with higher degrees. Right? And if we are having such kinds of polynomials, it is possible that we are getting such kinds of complex decision boundaries. Right? It is possible. Okay? Just understand this concept right now. We are going to focus upon these concepts later once again. Okay? This was
Okay, ma'am.
just to convey you the concept of decision boundary, and with respect to logistic regression and the hypothesis of the logistic regression, how it is possible to come up with either the linear decision boundary or the non-linear decision boundary. Right? So I hope you must have understood this concept.
Yes, ma'am.
Okay. So this was related to decision boundaries. Now, next, we are going to talk about the cost function for logistic regression. And what is this cost function? if we compare logistic regression with the linear regression that we have studied, in the linear regression, we have defined our cost function j of theta 0, theta 1. And that cost function j of theta 0, theta 1 was computed based on the sum of squared error. Am I correct? That was the cost function or the objective function for our linear regression, j of theta 0, theta 1. And we computed that j of theta 0, theta 1 by making use of the error, sum of squared error. Correct? Or mean of sum of squared error. Right? And we used that as the cost function, and we tried to minimize that cost function by making use of gradient descent. That is what we did for linear regression. Okay? Now, in linear regression, we had cost function which is sum of squared error. Now, let us see how to define the cost function for logistic regression. So, once again, I am stating our problem. Okay. In our training set, we are having n number of examples. And these examples are being denoted as x1, y1, x2, y2 up to xm, ym. So these are m examples in our training data set. So x denotes the input feature vector and y denotes the associated class label. Right? So x1, y1 is meant for the first example, x2, y2 is meant for the second example, and so on. So we are having total n number of examples in our training set. And every feature vector has n features. Every feature vector has n features. Okay? If we look at our feature vector x, we are having these features from x1 to xn, and as we know, we have added one more extra feature, that is x0, and that is always equal to 1. So overall, my feature vector x is of dimension n plus 1. Right? So n features, those are provided, and we have added one more feature x0 equal to 1. Right? So overall size of my feature vector is n plus 1. So n plus 1 elements are there in our feature vector x. Okay? x0 is always 1, and our label y is always having the value 0 or 1, because we are talking about the binary classification with two classes. So I am having class label either 0 or I am having class label as 1. Right? So this is what our problem statement is. Now, our hypothesis for logistic regression is of the form h theta x equal to 1 divided by 1 plus e to the power minus theta transpose x. So this is our hypothesis that we have seen, h theta x equal to 1 divided by 1 plus e to the power minus theta transpose x. This is our hypothesis. Now, what we would like to do is, we would like to choose the parameters theta, and that is what our goal is. Right? So we need to automatically come up with these parameters theta that will define my hypothesis h theta x. And this hypothesis h theta x is actually helping me to find out our decision boundary. Right? So we are going to answer now this question, how to choose parameters theta. Now, to choose the parameters theta, what is important is we should come up with a cost function. Right? We should come up with a cost function. So, as I mentioned, in linear regression, we had the cost function g of theta like this. We had a cost function like 1 divided by 2m summation over I equal to 1 to m h theta xi minus yi square. Okay, so for the sake of convenience, what we have done is, we have, instead of writing 1 divided by 2m, this half is taken inside the summation. The meaning is same. Okay, so in linear regression, we have come up with this cost function g of theta. Correct? Now, instead of having this cost function similar to that of linear regression, what we are going to do is, whatever is this term, instead of this term in our linear regression, right, we are going to say that the cost in logistic regression is defined as cost of h theta xi comma yi. So h theta xi is my prediction and yi is my actual label. So I am defining here a new function kind of a thing, and this function is based on this predicted value and the actual value of y. Right? So let us assume that this entire thing gets replaced with cost of h theta xi yi. Right? And please remember that our hypothesis h theta is not similar to that of linear regression, but our hypothesis h theta x is of this form, 1 divided by 1 plus e to the power minus theta transpose x. Right? Now, if by making use of this hypothesis, if I try to compute the cost in the similar way that I did for linear regression, then due to the nature, non-linear nature of my hypothesis h theta x, right, my g of theta will be a non-convex function like this, non-convex function. Right? In linear regression, we had a linear function, and that is why we mentioned that our cost function was always convex function of this form, a bowl-shaped function. And if I am having such kind of a convex function, then I may assure that I am having one global minima, and my gradient descent will take me to this global minima, and it is possible for me to come up with the optimal values of theta. But if I apply the similar kind of linear regression cost function to this hypothesis or with this hypothesis for my logistic regression, then I may have a very non-convex function, very non-convex cost function of this nature, right? And it is not possible for my gradient descent to reach to a global minima, because here I am having several local minimas, right? So the inference is the cost function similar to that of my linear regression cannot be used for logistic regression. I'll repeat. The cost function that is similar to that of linear regression cannot be applicable for logistic regression. And the reason is, in our linear regression, our hypothesis was linear. In logistic regression, our hypothesis is of the form 1 divided by 1 plus e to the power minus theta transpose x. Right? And if we plug in this kind of hypothesis over here, and if I try to compute my cost function, I may get the cost function g of theta with such kind of a nature. So such kind of a function I may get, which is a non-convex function. And if I try to minimize this function, my gradient descent will not ensure that we will always reach to the global minimum, because there are several local minimas are there, right? And this is why we should not go with the similar kind of cost function that we used for linear regression. Okay?
Ma'am,
Yes.
here our hypothesis is different. Then why it's coming like this non-convex? Means
See, my
we are already
hypothesis is different.
making. But ma'am, from hypothesis we start na. Then
Yes. Yes.
we'll go to cost function.
Of course. But
So
whenever we discussed linear regression, this hypothesis was linear in nature. And whenever we used the sum of squared error as the cost function, we have seen that our cost function was having such kind of a pattern, and this function was convex always for linear regression because our hypothesis was linear, right? And whenever we use this sum of squared error as our cost function, we end up with such kind of a convex function, and by application of gradient descent, it was possible for us to come up with the global minima, right? But as our hypothesis is now different, we cannot ensure that the sum of squared error similar to that of the linear regression, if I go with the similar kind of cost function, sum of squared error, it will not help me because my hypothesis is different. So I may come across such kind of a non-convex function, right, which is having several local minimas and not having the global minima. Okay, and that is why what we are claiming here is the cost function that was applicable for linear regression is not suitable for our logistic regression, and that is why we need to think of something else as our cost function, right? Because we want our cost function to be convex. If I'm having non-convex cost function, then it is not possible to reach to the global minimum. That is what our statement is right now. Okay, in the next session, we are going to extend this concept further and we'll see how to come up with a cost function for our logistic regression. Right?
okay, ma'am. Thank you.
Okay. So let's conclude today's session. You'll be having a quiz today. I'll be posting the link and all should respond for the quiz. The link will be open till 1:30 p.m. Okay? Fine. Thank you.